For centuries, Polaris has been the most reliable star in the night sky. Known as the North Star, it appears almost perfectly fixed above Earth's northern axis, while the rest of the sky slowly rotates around it. Sailors, explorers, and travelers have used it for navigation for hundreds of years. But Polaris hides a strange secret. When astronomers began studying it carefully, they discovered something unexpected. The star doesn't behave the way stellar physics predicts. Polaris is a cepheid variable, a type of star that expands and contracts in a predictable rhythm. These stars are so reliable that astronomers use them to measure distances across the universe. Except Polaris isn't following the rules. Its pulsations have changed in ways scientists didn't expect. Its mass doesn't perfectly match theoretical models, and over time, its brightness has behaved in ways that still puzzle astronomers today. All of this has led scientists to something known as the Polaris Paradox, because the star that has guided humanity for centuries may actually be one of the strangest stars in the sky. If you enjoy calm, immersive space documentaries like this, consider subscribing to Theories Before Sleep. On a clear night in the Northern Hemisphere, if you step outside and look toward the north, you may notice something unusual about the sky. Thousands of stars slowly drift across the darkness as the Earth rotates. Constellations rise and set. Patterns of light shift hour by hour. The entire sky appears to turn like a giant celestial wheel. But one star behaves differently. Near the center of that turning sky sits a single point of light that barely moves at all. That star is Polaris. For centuries, Polaris has been known as the North Star, a reliable beacon that seems fixed in place while the rest of the heavens rotate around it. Long before modern astronomy existed, people noticed this strange stability. While other stars rose and fell with the passing hours, Polaris remained almost perfectly still. It pointed north. Because of that, it became one of the most important stars in human history. Ancient navigators depended on it. Sailors crossing vast oceans used Polaris to determine their direction when there were no landmarks to guide them. Explorers traveling across deserts and wilderness used it to stay oriented at night. Even without instruments, Polaris provided a dependable reference point in the sky. But this remarkable stability is not because Polaris is actually motionless. The truth is more subtle. Polaris appears stationary because of its position relative to Earth's rotation. Our planet spins on an axis that runs from the North Pole to the South Pole. If you extend that axis into space, it points toward a small region of the sky, known as the North Celestial Pole. Stars near this point appear to circle around it as the Earth rotates, and Polaris happens to lie extremely close to that position. Because of this alignment, it appears almost fixed while the rest of the sky rotates around it. In reality, Polaris does move, but only slightly. Over the course of the night, it traces a tiny circle around the true celestial pole. The motion is so small that to the naked eye, it appears perfectly still. This special position is what made Polaris so valuable for navigation. Finding north is simple when Polaris is visible. All you need to do is locate the constellation Ursa Major, commonly known as the Big Dipper. Two of its stars form a line that points directly toward Polaris. Follow that line across the sky and you arrive at the North Star. Once Polaris is found, the direction of true north becomes immediately clear. But Polaris holds another useful secret. Its height above the horizon tells you your latitude. If Polaris sits 40 degrees above the horizon, you are roughly at 40 degrees north latitude on Earth. If it rises higher in the sky, you are further north. If it sinks lower, you are closer to the equator. This simple relationship allowed sailors to determine their position on the globe long before modern navigation systems existed. For generations, Polaris guided human exploration. Yet despite its importance, Polaris itself remained poorly understood for much of history. To early observers, it appeared to be nothing more than a steady star marking the north. But as telescopes improved and astronomy advanced, scientists began to discover that Polaris was far more complex than anyone had imagined. One of the first surprises came when astronomers measured its distance. Polaris lies about 433 light-years away from Earth. That means the light we see tonight left the star more than 4 centuries ago, long before modern science existed. In cosmic terms, this is relatively close. The Milky Way galaxy is over 100,000 light-years across, and many stars visible to the naked eye lie far further away than Polaris. Yet despite its relative proximity, Polaris is not an ordinary star like our Sun. It is far larger and far more powerful. Polaris is classified as a yellow supergiant. This type of star represents a late stage in stellar evolution, when a star has exhausted much of the hydrogen fuel in its core and begins to expand dramatically. Compared to the Sun, Polaris is enormous. Its radius is roughly 45 times larger than the Sun's. If Polaris were placed at the center of our solar system, its outer layers would extend far beyond the orbit of Mercury, and its brightness is astonishing. Polaris shines with about 2,500 times the luminosity of the Sun. Despite this tremendous output of energy, Polaris does not appear overwhelmingly bright in our sky because of its great distance, but its size and power reveal that Polaris is a star undergoing dramatic internal changes. These changes occur deep within the star's core, where nuclear fusion continues to transform lighter elements into heavier ones. Like all stars, Polaris exists in a delicate balance. Gravity pulls its massive outer layers inward, while energy from nuclear fusion pushes outward. As long as these forces remain balanced, the star remains stable. But in certain stars, that balance becomes unstable, and when that happens, the star begins to pulsate. This leads us to one of the most important discoveries about Polaris. Polaris is not just a supergiant star, it is a cepheid variable. Cepheid variables are a special class of stars that rhythmically expand and contract. As the star expands, its outer layers cool slightly and its brightness changes. When it contracts again, the temperature rises and the brightness shifts once more. This process creates a repeating cycle of pulsation. These cycles are extremely regular. Some cepheid stars complete a pulsation every few days. Others may take weeks. And the remarkable thing about these stars is that their pulsation period is directly related to their intrinsic brightness. The longer the pulsation period, the brighter the star truly is. This relationship was discovered in the early 20th century by astronomer Henrietta Swan Levitt, and it became one of the most powerful tools in astronomy. By measuring the pulsation period of a cepheid variable, astronomers can determine its true brightness. Then, by comparing that true brightness with how bright the star appears from Earth, they can calculate its distance. This technique allowed astronomers to measure distances far beyond our solar system. In fact, cepheid variables helped scientists determine the scale of the Milky Way galaxy. They also helped prove that distant spiral nebulae were actually separate galaxies far beyond our own. In other words, cepheid variables helped reveal the true size of the universe. Because of this, they are sometimes called cosmic distance markers, and Polaris happens to be one of them. But here is where things start to become strange. Polaris does not behave like a typical cepheid variable. Its pulsations are unusually weak. Most cepheid stars vary noticeably in brightness as they expand and contract, but Polaris changes only slightly, so slightly that early astronomers struggled to detect the pulsation at all. And over time, something even stranger began to happen. The pulsations of Polaris started to fade. During the 20th century, astronomers carefully tracked the brightness variations of the star. Year after year, the changes grew smaller. Some scientists even predicted that Polaris might eventually stop pulsating entirely. If that happened, it would be extremely unusual. Cepheid variables are expected to maintain their pulsation cycles for long periods of time during certain phases of stellar evolution. But Polaris seemed to be slowly abandoning that behavior. For a while, it looked as if the North Star might be transitioning into a completely stable star. Then something unexpected happened. Instead of disappearing, the pulsations began to grow again. Measurements showed that the brightness variations of Polaris were increasing once more. The star had reversed its trend. No one had predicted this. The star that appeared so stable in the sky was behaving unpredictably deep inside. And this was only the beginning of the mystery. As astronomers gathered more precise measurements of Polaris, additional inconsistencies began to appear. The star's mass did not match theoretical expectations. Its temperature seemed unusual for a star of its size, and its evolutionary stage did not perfectly align with models of how cepheid variables should behave. These discrepancies puzzled astronomers. If our understanding of stellar physics was correct, Polaris should behave in a certain way. But it didn't. This contradiction would eventually become known as the Polaris Paradox, a star that appears steady and reliable to the naked eye, yet behaves unpredictably when studied in detail. And Polaris had another secret. It is not alone. Through careful observation with telescopes, astronomers discovered that Polaris is part of a multiple star system. At the center lies Polaris A, the bright supergiant we see in the sky. But orbiting this star are at least two companions. One of them, known as Polaris B, is a smaller star located a short distance away from the main star. Polaris B can be seen through small telescopes as a faint companion to the North Star. The second companion, called Polaris AB, is much closer and far harder to detect. It orbits extremely close to Polaris A and was only confirmed using advanced observational techniques. These stars move slowly around each other, bound together by gravity. Their interactions may influence the behavior of the system in subtle ways. But even taking these companions into account, the strange properties of Polaris remain difficult to explain. Its pulsations remain unusual. its mass measurements remain uncertain, and its evolution does not perfectly match our models. All of this suggests that Polaris may be passing through a very rare stage of stellar evolution, one that astronomers have not fully understood. The irony of this mystery is remarkable. One of the most familiar stars in the sky, a star that guided travelers for centuries, may also be one of the least understood. Every night, Polaris quietly marks the direction of north. Yet behind that steady point of light lies a complex astrophysical puzzle. A puzzle that challenges what we know about how stars live, evolve, and change over time. And the deeper astronomers look, the more questions Polaris seems to raise, because the star that appears so perfectly stable in our sky may actually be undergoing dramatic changes deep within its core. In the next part, we will explore the strange pulsations of Polaris in greater detail, and why the North Star refuses to behave like other cepheid variable stars. When astronomers first began studying Polaris with modern instruments, they expected to see something fairly predictable. After all, Polaris belongs to a well-known class of stars called cepheid variables. These stars are famous for their rhythmic pulsations, a steady cycle of expansion and contraction that causes their brightness to rise and fall with remarkable precision. For over a century, cepheid variables have been among the most reliable tools in astronomy. Their behavior is so predictable that astronomers use them as cosmic measuring sticks, helping to determine distances across the universe. But Polaris, the most famous cepheid in the sky, refuses to behave normally. To understand why, we need to understand what actually causes a cepheid star to pulsate. Deep inside these stars, powerful physical processes are constantly at work. A cepheid variable does not pulsate because it is unstable in the way a dying star might explode. Instead, the pulsation is caused by a delicate balance between gravity and energy flowing outward from the star's core. Inside the star, layers of gas heat up, expand, cool, and contract in a repeating cycle. One of the key drivers of this process involves ionized helium. In certain layers of the star, helium atoms lose electrons when temperatures rise. This process changes how the gas absorbs and traps radiation. When helium becomes ionized, the gas becomes more opaque, trapping energy inside the star. This trapped heat causes the outer layers of the star to expand. As the star expands, the gas cools. When the gas cools enough, the helium recombines with electrons and becomes less opaque again. Suddenly, the trapped radiation escapes more easily, causing the outer layers to lose energy. Gravity then pulls those layers inward again. The star contracts. As it contracts, the gas heats up once more, ionizing helium again, and the entire process repeats. Expand, cool, contract, heat, over and over again. This cycle creates the rhythmic pulsations observed in cepheid variable stars, and these pulsations are remarkably stable. In most cepheids, the brightness changes in a predictable pattern, repeating with clock-like regularity. Some cepheids pulse every few days. Others take weeks or even months to complete a full cycle. But regardless of the exact period, their behavior follows well-understood physical laws, which is why Polaris is so confusing. Because Polaris does not pulse the way a normal cepheid should. The North Star does pulsate, but its pulsations are unusually weak. Compared to many cepheid variables, Polaris shows only tiny changes in brightness. Early astronomers struggled to detect the variation at all. At first, this seemed like a minor curiosity, but as astronomers began measuring Polaris more precisely, they noticed something deeply strange. The pulsations of Polaris were changing over time. In the early 20th century, astronomers observed that the brightness variations of Polaris were slowly shrinking. Year after year, the pulsations grew weaker. By the mid-1900s, the amplitude of the pulsation had dropped dramatically. Some scientists believed the star might eventually stop pulsating altogether. This would have been extremely unusual. Cepheid variables typically maintain their pulsations throughout specific stages of their evolution. The idea that Polaris might simply stop pulsating raised serious questions about how the star was evolving. But then, in the late 20th century, the trend suddenly reversed. Instead of continuing to weaken, the pulsations began growing stronger again. Astronomers were stunned. The star that seemed to be stabilizing had changed direction. Polaris had started pulsing more strongly once again. This unexpected reversal became one of the central mysteries of the Polaris Paradox. Something inside the star was changing, but scientists were not entirely sure what. Part of the confusion comes from Polaris's position in stellar evolution. Stars like Polaris spend most of their lives converting hydrogen into helium inside their cores. This process, known as hydrogen fusion, provides the energy that keeps the star stable. But eventually, hydrogen in the core becomes depleted. When that happens, the star must change. The core begins to contract under gravity, while the outer layers expand dramatically. The star grows larger and brighter, entering the supergiant phase of its life. Polaris is currently in this stage, but the exact evolutionary path of a cepheid variable can be complicated. In many cases, stars pass through the instability strip of the Hertzsprung-Russell diagram, a region where pulsations occur, more than once during their lifetime. A star may enter this region, begin pulsating, then evolve out of it before later crossing the region again. Each crossing produces different pulsation characteristics. Some astronomers believe Polaris may currently be undergoing one of these transitions, but determining exactly which stage Polaris is in has proven difficult. Measurements of the star's temperature, brightness, and pulsation period don't all agree with theoretical models. Some data suggest Polaris is crossing the instability strip for the first time. Other evidence indicates it may already have passed through once before. If Polaris is indeed moving through this region of stellar evolution, its pulsations could naturally change over time. But even this explanation does not fully account for the strange behavior observed. Another piece of the puzzle involves the period of the pulsation itself. Cepheid variables not only change brightness, their pulsation period can also shift slightly as the star evolves. As a star expands or contracts over long timescales, the period of its pulsation changes accordingly. Astronomers have been tracking the pulsation period of Polaris for more than a century, and they discovered that the period is increasing, slowly but steadily. This suggests that Polaris is expanding. In other words, the star itself is gradually growing larger over time. Such changes are expected in evolving stars. but the rate of change in Polaris appears faster than models predict. The star may be evolving more rapidly than astronomers anticipated. Yet even this does not fully explain the odd behavior of its pulsations. And there is another factor complicating the mystery. Polaris is not a single star. It is part of a multiple star system. At the center of the system lies Polaris A, the bright supergiant visible to the naked eye. Orbiting it is a smaller companion star known as Polaris AB, located extremely close to the main star. Further away lies Polaris B, a more distant companion that can be seen with telescopes. These stars orbit one another over long periods of time, bound together by gravity. The presence of companion stars can influence the evolution of a system in subtle ways. Gravitational interactions can affect the internal structure of stars. Over long timescales, tidal forces may alter rotation rates or influence mass transfer between stars. Some astronomers have suggested that the unusual pulsations of Polaris might be connected to these interactions. But so far, no definitive explanation has emerged. Adding to the mystery is the possibility that Polaris has changed brightness dramatically in the past. Some historical records suggest that ancient astronomers described Polaris as a much dimmer star than it appears today. If those records are accurate, Polaris may have brightened significantly over the last 1,000 years. However, interpreting ancient astronomical descriptions is difficult. Historical observations were often recorded in poetic language rather than precise measurements. Still, the idea that Polaris could be changing on human timescales is fascinating. Stars typically evolve over millions or billions of years, yet Polaris may be showing signs of evolution that we can observe within a single century. And if that is true, astronomers may be witnessing an unusually rapid phase of stellar evolution. The deeper scientists look, the more complicated Polaris appears. Its pulsations are weaker than expected. Their strength has changed dramatically over time. Its pulsation period is increasing, and its physical properties do not perfectly match theoretical predictions. Taken together, these observations have created one of the most intriguing stellar puzzles in modern astronomy. A star that should behave predictably, but doesn't. And perhaps the most remarkable aspect of this mystery is its location. Polaris is not hidden deep within the Milky Way. It is not buried inside a distant galaxy. It is one of the brightest and most familiar stars in the sky. Every night it shines quietly above the northern horizon, appearing calm and stable to anyone who looks up. But beneath that steady glow, powerful forces are constantly at work. Layers of gas expand and contract. Energy flows outward from nuclear reactions deep within the core. Gravity pulls inward on the star's enormous mass, and the entire star slowly evolves as it ages. In the next part, we will explore another surprising discovery about Polaris, one that made astronomers realize the North Star is not just strange, but far more complex than anyone once imagined. Because Polaris is not alone. It is part of a dynamic system of multiple stars orbiting one another across vast distances in space. And understanding that system may hold the key to solving the mystery of the Polaris Paradox. For most of human history, Polaris was thought to be a single star. To the naked eye, it appears as a solitary point of light marking the northern sky. Unlike many bright stars that form clear patterns in constellations, Polaris stands quietly at the end of the Little Dipper's handle, seemingly alone. But modern astronomy has revealed something surprising. Polaris is not a single star at all. It is part of a multiple star system, a small family of stars bound together by gravity and slowly orbiting one another in space. This discovery added an entirely new layer of complexity to the mystery surrounding the North Star. At the center of the system lies Polaris A, the bright yellow supergiant visible from Earth. This is the star responsible for the pulsations and unusual behavior that astronomers have been studying. But Polaris A has companions. The first of these companions is known as Polaris B. Polaris B lies a short distance away from the main star and can be seen through small telescopes as a faint point of light beside Polaris. While Polaris A dominates the system with its enormous size and brightness, Polaris B is a far smaller and more typical star. It is classified as a main sequence star, meaning it is still in the stable phase of its life, where hydrogen fusion occurs steadily in its core. Compared to the giant Polaris A, Polaris B is relatively modest. But the real surprise lies even closer to the main star. In 2006, astronomers confirmed the existence of a third star in the system, Polaris AB. Unlike Polaris B, which can be seen with telescopes, Polaris AB lies extremely close to the main star. Its presence was discovered through careful measurements of the motion of Polaris A. As Polaris A moves through space, it shows tiny shifts in its motion, subtle wobbles caused by the gravitational pull of a nearby companion. These shifts revealed that Polaris AB is orbiting the main star at a relatively close distance. Detecting Polaris AB was extremely challenging. The brightness of Polaris A overwhelms nearby objects, making direct observation difficult. But advanced instruments and techniques allowed astronomers to confirm that the star exists. This means that Polaris is actually a triple star system. Polaris A, the giant cepheid variable, Polaris AB, a close companion orbiting nearby, and Polaris B, a more distant star slowly circling the pair. These stars move together through the galaxy, bound by gravity in a delicate gravitational dance, and their interactions may play an important role in the strange behavior of Polaris. Understanding multiple star systems is crucial in modern astronomy. Many stars in our galaxy are not solitary like the Sun. In fact, a large percentage of stars exist in binary or multiple systems where two or more stars orbit each other. These systems can influence stellar evolution in powerful ways. When stars orbit close to one another, their gravitational pull can distort each other's outer layers. In some cases, stars may even exchange material through a process known as mass transfer. This can dramatically alter the life cycle of a star. But in the case of Polaris, the interactions are less extreme. Polaris AB is relatively small compared to the massive supergiant Polaris A. While it exerts gravitational influence, it does not appear to be stripping material from the larger star. However, its presence still matters, because when astronomers measure the mass of Polaris, they must account for the gravitational effects of its companions. And here is where another puzzle emerges. The mass of Polaris A does not perfectly match theoretical predictions. Stellar evolution models estimate that Polaris should have a certain mass based on its brightness, temperature, and pulsation behavior. But measurements derived from its orbital motion suggest slightly different values. In simple terms, Polaris appears to weigh either more or less than expected, depending on how the data are interpreted. This discrepancy may seem small, but in astrophysics, it is significant. Mass is one of the most important properties of a star. It determines how the star forms, how it evolves, how long it lives, and how it eventually dies. If the mass of Polaris does not match our models, it suggests that something about the star's evolution may be different from what we currently understand. One possible explanation involves stellar evolution timing. Polaris may be passing through a phase of evolution that occurs relatively quickly in astronomical terms. Stars spend millions or billions of years in stable stages of their life cycle, but certain transitional phases can occur much faster. If Polaris is currently undergoing such a transition, its physical properties could be shifting in ways that make it difficult to classify. Another possibility involves past interactions with its companions. If Polaris once exchanged mass with another star earlier in its life, that event could have altered its structure and evolution. While there is no direct evidence of such an interaction yet, astronomers continue to investigate the possibility. The presence of multiple stars also complicates observational measurements. When astronomers analyze light from Polaris, they must carefully separate the contributions from each star in the system. Even slight contamination from companion stars can affect measurements of brightness, temperature, and motion. Modern telescopes and space observatories have helped improve these measurements. For example, the Hubble Space Telescope has been used to observe Polaris and its companions in remarkable detail. High-resolution images have allowed astronomers to track the motion of Polaris AB as it orbits the main star. These observations provide valuable information about the system's structure. By measuring the orbital motion of Polaris AB, astronomers can estimate the mass of Polaris A more accurately. But even with these advanced tools, uncertainties remain. The Polaris system is complex, and fully understanding its dynamics requires extremely precise measurements over long periods of time. The orbit of Polaris AB, for example, takes about 30 years to complete. This means astronomers must track the star's motion for decades to fully map the system. And while Polaris B orbits much farther away, its movement through space also contributes to the overall gravitational balance of the system. These long timescales make stellar astronomy a slow but fascinating science. Researchers may spend entire careers studying the gradual changes of a single star. And Polaris, with all its strange behavior, has become one of the most intriguing targets in modern stellar research. But the mystery of Polaris does not end with its companions. Another surprising discovery involves the size and structure of the star itself. Using advanced techniques such as interferometry, a method that combines light from multiple telescopes to simulate a much larger instrument, astronomers have been able to measure the diameter of Polaris with remarkable precision. These measurements reveal that Polaris is not only enormous, but also slightly asymmetric. In other words, the star may not be perfectly spherical. This can happen when stars rotate or when pulsations distort their outer layers. Cepheid variables expand and contract as they pulsate, which can create temporary distortions in their shape. If Polaris is undergoing complex pulsations, or interacting gravitationally with its companions, these effects could become even more pronounced. Understanding these details requires incredibly sensitive observations, and each new measurement adds another piece to the puzzle. The more scientists study Polaris, the more they realize that the North Star is far more complicated than anyone once imagined. A massive pulsating supergiant, part of a multiple star system, possibly evolving in an unusual way, and perhaps even changing on timescales that humans can observe. All of this makes Polaris one of the most fascinating stars in the night sky. Yet from Earth, it still appears calm and steady. Night after night, it marks the direction of north, just as it has for centuries. To anyone looking up, it seems like the most stable star in the heavens. But hidden beneath that steady glow is a complex astrophysical system filled with motion, gravity, and evolving stellar processes. And as astronomers continue to study Polaris with increasingly powerful telescopes, they are beginning to uncover an even deeper mystery. Because the strange behavior of the North Star may not only challenge our understanding of cepheid variables, it may also reveal something new about how massive stars evolve and change over time. In the next part, we will explore another remarkable discovery about Polaris, evidence that the North Star may be evolving faster than astronomers once believed, revealing changes in real time that are rarely seen in stars. When we look at the night sky, the stars appear timeless. They shine quietly above us, seemingly unchanged from year to year, century to century. Entire civilizations have risen and fallen under the same constellations, and to the human eye, the heavens appear almost perfectly stable. But in reality, stars are constantly evolving. They are born from clouds of gas and dust. They grow, they age, and eventually they die. These processes take place over immense stretches of time, often millions or billions of years. Because of these enormous timescales, stellar evolution usually unfolds far too slowly for humans to witness directly. Astronomers typically study stars by observing many different examples at different stages of life. By comparing them, scientists reconstruct the life cycle of stars, but occasionally, nature offers something extraordinary, a star that changes quickly enough for us to observe its evolution within a human lifetime, and Polaris may be one of those rare cases. Over the past century, astronomers have noticed subtle but unmistakable changes in the North Star. One of the most important clues comes from the period of its pulsations. As we explored earlier, Polaris is a cepheid variable star. This means its outer layers expand and contract in a repeating cycle, producing rhythmic changes in brightness. Each cycle takes about 4 days to complete, but this period is not perfectly constant. Careful measurements show that the pulsation period of Polaris is gradually increasing. In other words, each pulsation cycle is taking slightly longer than the last. This may sound like a small change, but in stellar physics, it carries important meaning. The pulsation period of a cepheid variable is directly related to the size of the star. Larger stars pulsate more slowly. Smaller stars pulsate more quickly. If the pulsation period of Polaris is increasing, it means the star itself is growing larger. The outer layers of the star are slowly expanding, and that expansion tells astronomers something profound about the star's evolution. Polaris appears to be moving through a transitional stage of stellar development, a phase where its internal structure is changing. Deep inside the star, nuclear reactions continue to reshape its core. As hydrogen fuel in the core becomes depleted, the core contracts under gravity while the outer layers expand outward. This transformation can cause dramatic changes in the star's size, temperature, and brightness. In many stars, these changes occur gradually over millions of years, but Polaris may be evolving more rapidly than expected. The measured increase in its pulsation period suggests that the star is expanding at a measurable rate. Some estimates indicate that Polaris is increasing its pulsation period by several seconds each year. Over decades, that change becomes significant. It means astronomers are witnessing real-time evolution in a star hundreds of light years away. This is incredibly rare. Few stars change quickly enough for such effects to be observed within a human lifetime. Yet Polaris may be one of those exceptional cases. But the surprises don't stop there. Another fascinating clue comes from the temperature of the star. As stars expand, their outer layers typically cool. This is why red giant stars appear cooler and redder than smaller stars, like our Sun. Polaris, however, is classified as a yellow supergiant, meaning it occupies a region of stellar evolution between hot blue stars and cooler red giants. Its surface temperature is around 6,000 Kelvin, not drastically different from the Sun. Yet its enormous size makes it far more luminous. Because of its position in stellar evolution, Polaris lies within a special region of the Hertzsprung-Russell diagram known as the Instability strip. This region is where cepheid variables exist. Stars crossing this region become unstable and begin pulsating. But stars do not remain in this region forever. As they evolve, they move through the instability strip and eventually leave it. And the direction of that movement affects how their pulsations behave. Astronomers believe Polaris may currently be crossing the instability strip, but exactly which crossing remains uncertain. Some stars cross this region 3 times during their evolution. The first crossing occurs when the star expands into a supergiant for the first time. Later, the star may contract slightly and cross the strip again in the opposite direction. Finally, during later evolutionary stages, it may expand again and cross the strip for a 3rd time. Each crossing produces different pulsation patterns, and determining which crossing Polaris is experiencing would help astronomers understand its current evolutionary state. But observations of Polaris have produced conflicting results. Some measurements suggest the star is undergoing its first crossing of the instability strip. If that is true, it would mean Polaris is rapidly evolving for the first time into a supergiant star. But other evidence suggests the star may be on its 3rd crossing, which would place it at a more advanced stage of evolution. The difficulty arises because Polaris does not behave exactly like typical cepheid variables. Its pulsation amplitude is unusually small, its brightness variations are weaker than expected, and its pulsation strength has changed dramatically over time. These unusual characteristics make it difficult to place Polaris precisely within stellar evolution models, and that uncertainty lies at the heart of the Polaris Paradox, a star that should fit neatly into our understanding of stellar physics, but refuses to do so. Yet there is another intriguing possibility. Some astronomers believe that Polaris may have undergone dramatic changes in brightness over the past 1,000 years. Historical records from ancient observers sometimes describe Polaris as a relatively faint star. But today, Polaris is one of the brightest stars in the northern sky. If those historical observations are accurate, it would mean Polaris has brightened significantly in historical times. However, interpreting ancient astronomical records is challenging. Descriptions of stars were often written in poetic language rather than precise measurements. Cultural differences also influenced how brightness was described. So while the idea that Polaris has dramatically brightened remains uncertain, it continues to intrigue astronomers. If Polaris has indeed changed brightness over historical timescales, it would represent an extraordinary example of stellar evolution unfolding before human eyes. But even without that possibility, the measurable changes in Polaris today are already remarkable. Astronomers have now observed more than a century of data showing that the star's pulsation period is increasing. This growing dataset allows scientists to track the star's evolution with increasing precision. Every new observation adds another point to the timeline of Polaris's transformation. And as telescopes become more powerful, the data continues to improve. Space-based observatories, such as the Hubble Space Telescope and other modern instruments, have helped refine measurements of Polaris's distance, brightness, and motion. Meanwhile, long-term monitoring programs continue to track its pulsations year after year. Together, these observations are gradually revealing the story of a star in transition, but the puzzle is not yet solved. Some aspects of Polaris still resist explanation. Its mass measurements remain uncertain. Its pulsation amplitude behaves unpredictably, and its evolutionary stage remains debated among astronomers. Each new piece of data answers some questions while raising others. This is the nature of scientific discovery. Every mystery solved reveals deeper mysteries beneath. And Polaris, the quiet North Star, has become one of the most intriguing stellar puzzles in modern astronomy. The irony is almost poetic. For centuries, Polaris symbolized stability, a fixed point in the sky, a guide for travelers navigating uncertain terrain. Yet the star itself may be undergoing profound internal changes, a massive celestial engine slowly evolving in ways we are only beginning to understand. And as astronomers continue to watch Polaris carefully, they may be witnessing something extraordinary, a star changing in real time. In the next part, we will explore one final piece of the Polaris mystery: how modern telescopes and space observatories are revealing new details about the star, and why solving the Polaris Paradox could transform our understanding of stellar evolution. For centuries, Polaris appeared to be a solitary beacon. When early observers gazed at the North Star through small telescopes, they saw a single bright point of light standing almost motionless in the sky. It seemed isolated, alone at the top of the celestial sphere. But as telescopes improved, astronomers began to discover something surprising. Polaris is not a single star. It is a multiple star system, a small family of stars gravitationally bound together, orbiting a common center of mass. And this stellar family may hold the key to solving some of the deepest mysteries surrounding the North Star. The story begins in the late 18th century. In 1780, the astronomer William Herschel, one of the most famous observers of the night sky, was studying Polaris with a powerful telescope of his time. Herschel had already discovered Uranus and catalogued thousands of stars and nebulae. While observing Polaris, he noticed a faint point of light very close to the bright star. This dim companion star was later named Polaris B. At first, astronomers were unsure whether Polaris B was truly associated with Polaris or simply a distant star that happened to lie along the same line of sight. But over time, careful observations showed that Polaris B moves through space together with Polaris. Both stars share the same proper motion across the sky. This confirmed that they are gravitationally linked, members of the same star system. Polaris B orbits far from the main star. The distance between Polaris A and Polaris B is enormous, roughly 2,400 astronomical units, which is about 2,400 times the distance between Earth and the Sun. To put this into perspective, Neptune orbits our Sun at a distance of only 30 astronomical units. So Polaris B lies far beyond the scale of our own solar system. At that distance, the orbital period of Polaris B around Polaris A may take tens of thousands of years to complete, but Polaris B is only part of the story. In the 20th century, astronomers discovered that Polaris itself, the bright star we see with the naked eye, is actually composed of two stars orbiting very close to each other. The primary star, the cepheid variable we have been discussing, is known as Polaris AA. The smaller companion star orbiting it is called Polaris AB. This pair forms a close binary system. Unlike Polaris B, which lies far away, Polaris AB orbits extremely close to the main star. The distance between Polaris AR and Polaris AB is only a few billion kilometers, roughly comparable to the distance between the Sun and Saturn. Because Polaris AR is so bright, Polaris AB remained hidden for centuries. The light of the primary star completely overwhelmed the faint glow of the smaller companion. Even powerful ground-based telescopes struggled to detect it. But modern astronomical technology eventually made the discovery possible. In the early 2000s, astronomers used the Hubble Space Telescope to observe Polaris with exceptional precision. By carefully analyzing images taken with Hubble's instruments, scientists were finally able to directly detect Polaris AB. This observation confirmed that Polaris is a triple star system. Three stars bound together by gravity. Polaris AA, the massive cepheid variable. Polaris AB, the close companion star. Polaris B, the distant outer companion. Understanding this stellar family has become crucial to solving the Polaris Paradox, because binary stars allow astronomers to measure something extremely valuable: mass. In astronomy, measuring the mass of a star is surprisingly difficult. For most stars, scientists must estimate mass indirectly using models of stellar evolution. But in binary systems, gravity provides a natural measuring tool. By observing how two stars orbit each other, astronomers can calculate their masses using Newton's laws of motion and gravity. This is one of the most reliable methods for determining stellar mass. And Polaris offers a rare opportunity to apply this technique. By tracking the orbit of Polaris AB around Polaris AA, astronomers can estimate the mass of the cepheid variable. And that measurement is extremely important. Cepheid variables follow a well-known relationship between their luminosity and pulsation period. This relationship makes them one of the most important tools in astronomy. Cepheids act as cosmic distance markers. By measuring the pulsation period of a cepheid star, astronomers can determine its intrinsic brightness. Then, by comparing that intrinsic brightness to how bright the star appears from Earth, they can calculate its distance. This method has been used to measure distances across our galaxy and even in distant galaxies. Cepheids helped astronomers determine the size of the Milky Way. They helped reveal that other galaxies exist beyond our own, and they played a crucial role in discovering the expansion of the universe. In fact, the famous astronomer Edwin Hubble used cepheid variables to prove that the Andromeda Nebula was actually a separate galaxy millions of light years away. Because cepheids are so important for measuring cosmic distances, astronomers want to understand them as precisely as possible. That means understanding their mass, structure, and evolution. And Polaris, being the nearest cepheid variable to Earth, is one of the most valuable stars for studying these questions. But when astronomers measured the mass of Polaris using the orbit of Polaris AB, they encountered something strange. The mass estimates did not match predictions from stellar evolution models. In simple terms, Polaris appeared to be lighter than expected. Theoretical models suggested the star should have a certain mass based on its brightness and pulsation behavior. But orbital measurements suggested a different value. This discrepancy became known as the cepheid mass problem, and Polaris sits right at the center of it. If astronomers cannot accurately determine the mass of a nearby cepheid, like Polaris, it raises questions about how well we understand these stars in general. And if our understanding of cepheids is incomplete, it could affect how accurately we measure distances across the universe. Fortunately, recent observations are helping to refine these measurements. Advanced telescopes and improved data analysis techniques have allowed astronomers to track the orbit of Polaris AB more precisely than ever before. The orbital period of Polaris AB around Polaris AA is estimated to be around 30 years. That means astronomers can watch a significant portion of the orbit unfold within a few decades. Each new observation adds more information about the star's motion. Over time, these measurements help refine estimates of the star's mass. Meanwhile, observations of Polaris B, the distant companion, provide additional clues. Because Polaris B shares the same motion through space as the main star, it confirms that the entire system formed together. This means all three stars likely formed from the same original cloud of gas and dust. Studying Polaris B can therefore reveal information about the system's age and chemical composition. And that information helps astronomers better understand the evolutionary history of Polaris itself. But the presence of multiple stars may also complicate the system. Gravitational interactions between stars in a multiple star system can affect their evolution. In some cases, stars can exchange mass with one another or influence each other's internal structure through tidal forces. Could interactions between Polaris AA and Polaris AB have altered the star's evolution? Could this explain some of the unusual behavior seen in Polaris's pulsations? Some astronomers believe it might. The presence of a close companion could influence the outer layers of the star, subtly affecting its pulsation patterns. It could even affect how the star loses mass through stellar winds. These possibilities remain active areas of research. The more astronomers learn about the Polaris system, the more complex the picture becomes. What once seemed like a single, simple star now reveals itself as a dynamic stellar family. 3 stars dancing slowly around one another through space, their gravitational interactions stretching across billions of kilometers. And at the heart of that system lies the famous North Star, a pulsating supergiant whose internal changes may be unfolding within a single human lifetime. Polaris may have guided sailors across unknown oceans, but now it is guiding astronomers toward deeper insights into how stars evolve. In the next and final part, we will explore how modern space missions, precision measurements, and future telescopes may finally solve the Polaris Paradox, and what the answer could reveal about the life cycles of stars across the universe. For thousands of years, Polaris has been humanity's most reliable star. Sailors trusted it to navigate across vast oceans. Travelers used it to determine direction long before compasses were common. Entire civilizations learned that the North Star marked the axis of the sky. But modern astronomy has revealed something astonishing. The star that once symbolized perfect stability may actually be one of the most mysterious stars in the night sky. Polaris is changing. Its pulsations are shifting. Its brightness has varied. Its mass measurements do not perfectly match theoretical predictions, and its evolutionary stage remains uncertain. This collection of puzzles has become known among astronomers as the Polaris Paradox. A star that should be simple, yet refuses to behave exactly as expected. But in the past 2 decades, a new generation of astronomical instruments has begun to shed light on this mystery. For most of history, astronomers studied stars using ground-based telescopes. These instruments were powerful, but they faced one major limitation: Earth's atmosphere. As starlight passes through the atmosphere, it is distorted by turbulence. This is why stars appear to twinkle when viewed from the ground. For centuries, this atmospheric distortion limited the precision of astronomical measurements. But space telescopes changed everything. By placing telescopes above Earth's atmosphere, astronomers gained a crystal-clear view of the universe, and Polaris became one of the stars studied with these powerful new tools. One of the most important missions in this effort is the Gaia spacecraft, launched by the European Space Agency in 2013. Gaia was designed to perform one of the most ambitious astronomical surveys in history. Its goal is to measure the positions, motions, and distances of more than 1 billion stars across the Milky Way, and it does so with extraordinary precision. Gaia can measure the position of a star to an accuracy equivalent to measuring the thickness of a human hair from thousands of kilometers away. One of the key techniques Gaia uses is called stellar parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. This tiny shift allows astronomers to calculate the distance to the star. It's the most direct and reliable method of measuring stellar distances. And distance is crucial for understanding Polaris, because if astronomers know exactly how far away Polaris is, they can determine its true brightness, size, and mass more accurately. For decades, the distance to Polaris has been debated. Early measurements suggested Polaris lies about 430 light-years away, but other studies proposed slightly different values. Even small differences in distance can significantly affect calculations of a star's luminosity and size. Gaia's measurements have begun refining these estimates, and with each new data release, astronomers gain a clearer picture of the Polaris system. But distance measurements are only part of the story. Modern telescopes are also revealing new details about Polaris's internal structure. One important tool in this effort is spectroscopy. When astronomers split starlight into its component colors, they can analyze the spectral lines produced by different elements. These lines reveal information about the star's temperature, composition, and motion. Spectroscopy allows scientists to measure how the surface of Polaris moves during its pulsation cycles. As the star expands and contracts, parts of its surface move toward or away from Earth. This motion slightly shifts the wavelengths of the star's light, a phenomenon known as the Doppler effect. By studying these shifts, astronomers can measure the speed of the pulsations with remarkable precision. These measurements provide valuable information about the internal physics of the star. They help scientists test models of stellar structure and energy transport, and Polaris, as the nearest cepheid variable star, serves as an ideal laboratory for this research. But perhaps the most exciting discoveries about Polaris may still lie in the future. A new generation of telescopes is now coming online that will revolutionize our view of the cosmos. Among them is the James Webb Space Telescope. Unlike earlier space telescopes, Webb observes the universe primarily in infrared light. Infrared wavelengths allow astronomers to peer through clouds of gas and dust that would otherwise obscure objects. This capability may allow scientists to study subtle details of Polaris's outer atmosphere and stellar winds. Meanwhile, massive ground-based observatories are being constructed that dwarf any telescope built before. The extremely large telescope, ELT, in Chile, will feature a mirror nearly 40 meters in diameter. That is larger than the width of a basketball court. With such enormous light-gathering power, astronomers will be able to study stars with unprecedented detail. These telescopes may allow scientists to observe structures in Polaris's atmosphere directly. They may even reveal how the star loses mass through stellar winds, an important process that influences the evolution of massive stars. And understanding Polaris is not just about solving a single stellar mystery. The implications reach much farther. Cepheid variable stars are among the most important tools in cosmology. Because their brightness is directly linked to their pulsation period, cepheids act as standard candles for measuring cosmic distances. Astronomers use them to measure distances to nearby galaxies. Those measurements help calibrate other distance indicators, such as Type 1a supernovae, and those supernovae are used to measure distances across vast regions of the universe. In fact, the discovery that the universe is expanding and accelerating ultimately depends on the accuracy of these cosmic distance measurements. So improving our understanding of cepheid variables directly affects our understanding of the size, age, and expansion rate of the universe. And Polaris, as the closest cepheid variable star, plays a critical role in refining these measurements. It is essentially the benchmark cepheid. If astronomers can fully understand Polaris, its mass, luminosity, pulsation behavior, and evolutionary stage, they can calibrate cepheid models with far greater accuracy. This, in turn, improves measurements across the entire cosmic distance ladder. In other words, solving the Polaris Paradox may help refine our understanding of the universe itself. But there is also something deeply poetic about this investigation. The North Star has guided humanity for thousands of years. It helped explorers cross oceans. It helped travelers find their way through unfamiliar landscapes. And now it is guiding astronomers toward deeper knowledge about the life cycles of stars. A single star, quietly shining in the northern sky, is helping scientists unravel the physics of stellar evolution and the scale of the cosmos. Yet even after centuries of observation, Polaris still holds secrets. Its pulsation amplitude remains unusual, its evolutionary path remains debated, and its long-term brightness changes remain an open question. Some mysteries may take decades more to solve, but that is the nature of science. Each generation of astronomers adds another layer of understanding, and slowly, the universe reveals its secrets. For now, Polaris remains both familiar and mysterious. To the naked eye, it is simply a steady point of light marking the northern sky. But behind that calm appearance lies a massive, evolving star, a stellar engine undergoing transformations that unfold across millions of years. And perhaps the most extraordinary fact of all is this: humanity may be living at the exact moment when those changes have become visible. A star that guided ancient sailors, a star that anchored the night sky, may now be revealing in real time the hidden processes that shape the life and death of stars. And every clear night, Polaris still shines above us, quiet, steady, seemingly unchanged. Yet deep inside, the North Star may be telling one of the most fascinating stories in modern astronomy. Today, Polaris feels permanent. Look north on any clear night in the northern hemisphere, and there it is, a steady point of light almost perfectly fixed in the sky. Every other star appears to circle around it. To the naked eye, Polaris seems like the anchor of the heavens. But the truth is far stranger. Polaris has not always been the North Star, and it will not remain the North Star forever. The idea that Polaris marks the north celestial pole is actually the result of a slow cosmic motion, a motion so gradual that most people never notice it during their lifetime. This motion is called axial precession. To understand it, imagine the Earth as a spinning top. When a top spins, its axis doesn't remain perfectly upright. Instead, it slowly wobbles in a circular motion. This wobble causes the direction of the top's axis to trace out a circle over time. Earth behaves in the same way. Our planet rotates once every 24 hours, but the axis of rotation itself slowly shifts direction over thousands of years. The cause of this wobble is gravity. The Sun and the Moon both exert gravitational forces on Earth. Because our planet is not a perfect sphere, it bulges slightly at the equator. Those gravitational forces pull unevenly on Earth's mass. Over time, this causes the axis of Earth to slowly change direction. But the change is incredibly slow. One complete cycle of Earth's axial precession takes about 26,000 years. This means the direction that Earth's axis points gradually traces a circle across the sky over millennia. And wherever that axis points, a different star becomes the North Star. Right now, Earth's axis happens to point very close to Polaris, but thousands of years ago, it pointed somewhere else entirely. To the ancient Egyptians, Polaris was not the North Star. During the time when the pyramids were being built, roughly 4,500 years ago, the closest bright star to the North Celestial Pole was a different star called Thuban. Thuban lies in the constellation Draco, the dragon. At that time, Thuban sat almost perfectly at the center of the rotating sky. For Egyptian astronomers and architects, Thuban may have served as a celestial reference point. Some researchers even believe the alignment of certain pyramids may have been influenced by the position of this ancient North Star. But the cosmic wobble continued. Over centuries, Earth's axis slowly drifted away from Thuban. Another star briefly took its place as the closest star to the pole. Then another, and eventually, around the medieval period, Polaris gradually moved into position near the pole. But Polaris did not become the true North Star overnight. The change happened slowly. During the time of the Roman Empire, Polaris was still several degrees away from the celestial pole. It was useful for navigation, but it was not perfectly centered. Over the next 1,000 years, however, Polaris slowly crept closer to the pole. By the time of the Great Age of Exploration, when sailors crossed oceans guided only by the stars, Polaris had become the most reliable marker of true north. It wasn't perfectly aligned, but it was close enough that navigators could use it to determine latitude with impressive accuracy. Sailors developed simple techniques for finding Polaris. First, they located the Big Dipper, one of the most recognizable star patterns in the northern sky. The two stars at the end of the Big Dipper's bowl, often called the pointer stars, form a line pointing directly toward Polaris. By extending that line upward into the sky, navigators could quickly locate the North Star. Once Polaris was identified, sailors could estimate their latitude by measuring the angle between Polaris and the horizon. If Polaris appeared high in the sky, they were far north. If Polaris appeared low near the horizon, they were closer to the equator. This method allowed explorers to navigate vast oceans long before GPS or modern instruments existed. But even Polaris's reign as the North Star is temporary. Earth's precession continues. Right now, Polaris lies less than 1 degree from the North Celestial Pole, but the axis of Earth is still drifting. In the year 2100, Polaris will reach its closest alignment with the pole. At that moment, it will sit almost perfectly above Earth's rotational axis. For a brief period in cosmic time, Polaris will truly be the North Star. But after that, the slow wobble of Earth will carry the pole away again. Over the next thousands of years, Polaris will gradually drift farther from the pole. Another star will take its place. One of the most famous future North Stars will be Vega, a brilliant blue-white star in the constellation Lyra. About 12,000 years from now, Vega will lie close to the North Celestial Pole. To observers living in that distant future, Vega will appear almost motionless in the sky, just as Polaris does today. And Polaris itself will become just another bright star slowly circling the pole each night. This constant shift reminds us of something profound. The night sky is not fixed. Although the stars seem eternal and unchanging, the cosmos is in constant motion. Earth rotates. Earth orbits the Sun. The Sun orbits the center of the Milky Way. And even the orientation of Earth's axis slowly evolves over time. Yet despite this motion, Polaris occupies a special place in human history. It has guided explorers, inspired myths, and anchored our understanding of the sky. Many cultures viewed the North Star as a symbol of stability and permanence. In Chinese astronomy, the region around the North Celestial Pole was associated with the celestial emperor, the ruler of the heavens. In Norse mythology, the pole star was sometimes imagined as the point around which the cosmic sky wheel turned. And in navigation traditions across the world, Polaris became a symbol of direction and guidance. But perhaps the most fascinating part of the story is this: even as Polaris serves as our guiding star, it is itself evolving. Deep within its core, nuclear reactions continue transforming hydrogen into helium. The star's outer layers expand and contract as it pulsates. Its brightness shifts, its structure changes, and over millions of years, Polaris will eventually exhaust its nuclear fuel and move toward the later stages of stellar evolution. One day, the North Star will become a completely different kind of object. But long before that happens, Earth's precession will have carried the North Celestial Pole far away. Future civilizations may look at the sky and wonder why ancient humans cared so much about a star called Polaris. To them, Vega, or some other star, will mark the north. This perspective reveals something extraordinary about astronomy. The sky we see today is only a snapshot in time, a temporary arrangement of stars shaped by the motion of Earth and the evolution of the cosmos. Polaris, the star that seems so steady tonight, is only the North Star for a brief moment in the grand timeline of the universe. Yet during that brief moment, it has become one of the most famous stars in the sky, a cosmic landmark, a navigational guide, and a mysterious cepheid variable star whose changing behavior continues to puzzle astronomers. The Polaris Paradox reminds us that even the most familiar objects in the night sky can hide unexpected secrets. And sometimes, the star that appears the most constant is actually one of the most dynamic objects we can observe. In the next part, we will explore one of the most intriguing questions about Polaris. What will happen to the North Star in the distant future, and how will its life eventually end? Polaris feels permanent. For anyone living in the Northern Hemisphere today, it seems as though the North Star has always been there, steady, unchanging, quietly marking the center of the sky. But like every star in the universe, Polaris has a beginning, and it will eventually have an end. Stars are not eternal. They are born, they evolve, and they die. The story of Polaris is only one chapter in a much longer cosmic life cycle that spans hundreds of millions of years. To understand the future of the North Star, we must first understand what Polaris really is. Polaris is not an ordinary star like our Sun. It is a yellow supergiant. Its mass is estimated to be roughly 5 to 6 times the mass of the Sun, and its radius is enormous, about 40 to 50 times larger than the Sun. If Polaris replaced the Sun in our solar system, its outer layers would extend far beyond the orbit of Mercury and possibly approach the orbit of Venus. Despite having a surface temperature similar to the Sun, its enormous size makes it vastly more luminous. Polaris shines with thousands of times the brightness of the Sun. This enormous energy output tells astronomers something important. Polaris is already well into the later stages of its stellar life. Stars spend most of their lives in a phase called the main sequence, where hydrogen in the core is fused into helium. For a star like the Sun, this phase lasts about 10 billion years, but more massive stars burn their fuel much faster. A star with 5 times the mass of the Sun may spend only 100 million years on the main sequence before exhausting its hydrogen supply. Polaris has almost certainly already passed through that stage. At some point in the past, the hydrogen in its core became depleted. When that happened, the balance between gravity and pressure inside the star began to shift. Gravity started pulling the core inward. As the core contracted, temperatures increased dramatically. Meanwhile, the outer layers of the star expanded outward. This transformation turned Polaris into the supergiant star we see today. During this stage of evolution, nuclear fusion moves into shells around the core. Hydrogen fusion may occur in a shell surrounding a helium-rich core. Eventually, the core itself may begin fusing helium into heavier elements such as carbon and oxygen. This phase of stellar evolution can be unstable. Changes in the star's internal structure cause the outer layers to expand and contract. And this is exactly what we observe in Polaris. Its rhythmic pulsations are the visible signature of internal changes deep within the star. But these pulsations will not last forever. As Polaris continues evolving, it will eventually leave the instability strip of the Hertzsprung-Russell diagram. When that happens, its pulsations will fade. The star will stabilize for a time as it enters the next phase of its life. But the long-term future of Polaris depends largely on one key factor: its mass. Mass determines the ultimate fate of every star. Small stars, like red dwarfs, burn slowly and quietly for trillions of years. Sun-like stars eventually expand into red giants before shedding their outer layers to form planetary nebulae. But very massive stars, those more than 8 times the mass of the Sun, end their lives in the most violent events in the universe: supernova explosions. So where does Polaris fall on this scale? Current estimates suggest Polaris has a mass slightly below the threshold required to explode as a supernova. If these estimates are correct, Polaris will likely follow a path similar to that of intermediate mass stars. Over the next millions of years, the star will continue expanding and cooling. It will probably evolve into a red supergiant with a surface temperature cooler than it has today and a radius even larger than its current size. During this phase, the outer atmosphere of the star will become increasingly unstable. Strong stellar winds will begin blowing material away from the star into space. Over time, Polaris may lose a significant portion of its mass through these winds. Eventually, the core of the star will become composed mostly of carbon and oxygen. At this point, nuclear fusion can no longer continue. The core will no longer produce the energy needed to counteract gravity. But unlike very massive stars, Polaris may not collapse catastrophically. Instead, the outer layers of the star will gradually drift away into space. This expanding shell of gas will become a planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. The term comes from early astronomers who thought these glowing clouds resembled small planets through their telescopes. In reality, planetary nebulae are some of the most beautiful structures in the cosmos. They appear as glowing shells of gas illuminated by the hot core of the dying star. Inside the nebula, the core of Polaris would remain as a dense stellar remnant known as a white dwarf. White dwarfs are incredibly compact. They contain roughly the mass of the Sun squeezed into an object about the size of Earth. Matter inside a white dwarf is compressed to extreme densities. A single teaspoon of white dwarf material would weigh tons on Earth. Once formed, a white dwarf no longer produces energy through nuclear fusion. Instead, it slowly cools over billions of years, radiating away the remaining heat from its former life as a star. If Polaris follows this path, its future will be peaceful compared to the explosive deaths of more massive stars. But the transformation will still be dramatic. The brilliant North Star we see today would disappear. In its place would remain a faint white dwarf surrounded by an expanding cloud of glowing gas. And even that nebula would eventually fade. Over tens of thousands of years, the gas would disperse into the interstellar medium, the vast clouds of gas and dust between stars. That material would then become part of the next generation of stars. In this way, the death of Polaris would help seed the galaxy with the raw ingredients for new stars and planets. But this future lies millions of years ahead. Long before Polaris reaches the end of its life, Earth itself will have changed dramatically. Continental plates will shift, mountains will rise and erode, species will evolve and disappear. Human civilization may transform in ways we cannot even imagine. And even sooner than that, Polaris will cease to be the North Star. As we explored earlier, Earth's axis is slowly wobbling. Over the next thousands of years, the North Celestial Pole will drift away from Polaris. Eventually, other stars will take its place as the marker of true north. By the time Polaris reaches the end of its life cycle, it will no longer hold that special position in the sky. It will simply be another aging star in the Milky Way. Yet its story will remain one of the most fascinating in astronomy, because Polaris has offered scientists something rare, a nearby cepheid variable star whose changes can be observed with incredible detail. Through Polaris, astronomers study stellar pulsations, stellar evolution, and cosmic distance measurements. The star that once guided sailors across oceans is now guiding astronomers through the physics of stars themselves. And perhaps that is the most remarkable legacy of the North Star. For thousands of years, Polaris helped humanity navigate the Earth. Now it is helping humanity navigate the universe, a quiet point of light in the northern sky, revealing the life cycle of stars, the structure of our galaxy, and the vast scales of cosmic time. And every clear night, Polaris still shines above us, a star that seems constant, yet is quietly evolving, just like the universe around it. At first glance, Polaris might seem like just another star. It shines in the northern sky, guiding travelers and marking direction. But in the vastness of the universe, it is only one star among hundreds of billions in the Milky Way. Yet Polaris holds an importance far beyond its brightness or its role in navigation. To astronomers, Polaris is one of the most valuable stars in the sky because it belongs to a special class of stars that changed our understanding of the universe. These stars are called cepheid variables. Cepheid variable stars are remarkable because they pulsate. Their outer layers rhythmically expand and contract, causing their brightness to rise and fall in a repeating cycle. Some cepheids pulse over a few days. Others take weeks or even months to complete a cycle. But the most extraordinary feature of cepheids is not the pulsation itself. It is the relationship between their pulsation period and their brightness. In the early 20th century, an astronomer named Henrietta Swan Levitt was studying photographs of the night sky taken at the Harvard College Observatory. Her work focused on stars in the small Magellanic Cloud, a nearby dwarf galaxy. Because all the stars in that galaxy lie roughly the same distance from Earth, differences in their apparent brightness must reflect differences in their true brightness. While examining these stars, Levitt discovered something astonishing. Cepheid variables with longer pulsation periods were intrinsically brighter than cepheids with shorter periods. This simple relationship became one of the most powerful tools in astronomy. By measuring how long a cepheid takes to pulse, astronomers can determine its true luminosity. Once they know the star's intrinsic brightness, they can compare it to how bright the star appears from Earth. The difference between those two values reveals the star's distance. This technique transformed astronomy. Before this discovery, astronomers had no reliable way to measure distances beyond our immediate stellar neighborhood. The universe beyond the Milky Way was largely mysterious, but cepheid variables changed that. In the 1920s, the astronomer Edwin Hubble used cepheid stars to measure the distance to the Andromeda Nebula. At the time, many scientists believed that these nebulae were simply clouds of gas within the Milky Way, but Hubble's measurements told a different story. The cepheid stars in Andromeda were far too distant to belong to our galaxy. They revealed that Andromeda was an entirely separate galaxy, a vast island of stars millions of light years away. This discovery expanded the known size of the universe almost overnight. Suddenly, the cosmos was far larger than anyone had imagined, and cepheid variables had made it possible. Polaris belongs to this same class of stars. That alone makes it important. But Polaris has another advantage. It is the closest cepheid variable to Earth. Because it is relatively nearby, astronomers can study it in extraordinary detail. Most cepheid variables are so distant that they appear only as tiny points of light in telescopes. But Polaris is bright and accessible. Scientists can measure its pulsations, analyze its atmosphere, track its motion through space, and even study the companion stars orbiting around it. This makes Polaris a benchmark cepheid. If astronomers can fully understand Polaris, its mass, luminosity, pulsation behavior, and evolutionary stage, they can calibrate the entire cepheid distance scale. And that calibration affects nearly every measurement of cosmic distance. Cepheids are used to measure distances to nearby galaxies. Those measurements help calibrate other distance indicators, including Type 1a supernovae. And Type 1a supernovae are used to measure distances across enormous regions of the universe. These measurements allow astronomers to determine one of the most important values in cosmology, the Hubble constant, which describes how fast the universe is expanding. The expansion of the universe is not just an abstract concept. It shapes the evolution of galaxies, the distribution of matter, and the fate of the cosmos itself. But measuring the expansion rate precisely has proven difficult. Different measurement techniques sometimes produce slightly different results. This discrepancy is known as the Hubble tension. One set of measurements, based on observations of the early universe using the cosmic microwave background, suggests a slightly slower expansion rate. Another set of measurements, based on nearby galaxies using cepheid variables and supernovae, suggests a faster rate. The difference is small, but significant. It may indicate that our understanding of the universe is incomplete. Some scientists believe the discrepancy could hint at new physics, perhaps new particles, new forces, or unknown aspects of cosmic expansion. But before drawing such conclusions, astronomers must ensure that the distance measurements themselves are accurate. And that brings us back to Polaris. Because Polaris is the nearest cepheid variable, it plays a crucial role in refining the cepheid distance scale. By measuring Polaris precisely, astronomers can test the relationship between pulsation period and luminosity with exceptional accuracy. If that relationship is even slightly different than expected, it could affect distance measurements across the universe. In other words, the behavior of a single star in the northern sky may influence our understanding of the entire cosmos. This is why solving the Polaris Paradox matters so much. Polaris behaves somewhat differently from many other cepheid variables. Its pulsation amplitude is unusually small. Its brightness changes have evolved over time, and its mass estimates do not perfectly match theoretical predictions. If astronomers cannot fully explain these differences, it raises questions about how representative Polaris is of other cepheid stars. Is Polaris unusual, or does it reveal a gap in our understanding of stellar physics? Researchers are working hard to answer these questions. Modern telescopes, space missions, and long-term monitoring programs continue collecting data on Polaris. Each new observation helps refine models of stellar evolution. At the same time, astronomers are studying cepheid variables in other galaxies to compare their behavior with that of Polaris. Large surveys now track thousands of cepheids across the Milky Way and beyond. These surveys help scientists identify patterns and refine the period-luminosity relationship. Meanwhile, the Gaia mission continues mapping the positions and distances of stars across our galaxy with unprecedented precision. Gaia's data helps calibrate the distances to nearby cepheid variables, including Polaris. This improves the foundation of the entire cosmic distance ladder. But even as new data arrives, Polaris continues to surprise astronomers. Its pulsation period continues to increase. Its amplitude remains unusual, and its evolutionary stage remains debated. Some astronomers believe Polaris may currently be crossing the instability strip for the first time. Others believe it may be on its third crossing. Each possibility carries different implications for stellar evolution models. But regardless of the final answer, Polaris has already played an extraordinary role in astronomy. It guided ancient sailors. It inspired myths and navigation traditions across cultures. And now it sits at the center of one of the most important scientific questions in cosmology. How far away are the galaxies? How fast is the universe expanding? And what does that expansion reveal about the nature of the cosmos? The answers to these questions begin with something surprisingly small: the rhythmic pulsation of a star. a star whose light travels more than 400 years to reach Earth, a star that appears steady to the naked eye, yet quietly expands and contracts every few days. Polaris, the North Star, a cosmic lighthouse that once guided ships across oceans and now guides humanity across the vast distances of the universe. In the final chapter of this story, we will step back and look at Polaris from a wider perspective, exploring why this single star continues to fascinate astronomers and what its mystery reveals about the ever-changing universe we inhabit. On any clear night in the Northern Hemisphere, you can find Polaris. Look toward the north. Follow the two pointer stars of the Big Dipper. Extend the line they form, and eventually, your eyes will land on a single, steady star. Unlike the others, it barely moves. The entire sky appears to rotate around it. To the naked eye, Polaris feels permanent, like a cosmic nail pinning the heavens in place. But after everything we have explored, we know something remarkable. Polaris is not permanent at all. It is changing, it is evolving, and the more astronomers study it, the more extraordinary its story becomes. For centuries, Polaris was simply the North Star. It was a tool for navigation, a reference point for direction, a symbol of stability in a sky that seemed eternal. Ancient travelers relied on it when crossing deserts. Sailors trusted it when navigating across open oceans. Entire cultures built myths and stories around this single star that appeared fixed above the northern horizon. Yet Polaris is only the North Star because of a cosmic coincidence. Earth's axis slowly wobbles in space in a motion called precession. Over thousands of years, this wobble causes the direction of the North Celestial Pole to drift across the sky. Right now, that wandering axis happens to point almost directly at Polaris. But it has not always done so. Thousands of years ago, a different star marked the north. Thousands of years from now, another star will take Polaris's place. The sky that seems fixed to us is actually moving on timescales far longer than human history, and Polaris itself is moving too. Deep inside the star, nuclear fusion continues reshaping its core. Its outer layers expand and contract every few days as it pulses like a slow cosmic heartbeat. Its pulsation period is gradually increasing. Its internal structure is evolving. In many ways, Polaris represents something rare in astronomy, a star whose evolution may be unfolding slowly enough for humans to observe. Normally, stellar evolution takes millions or billions of years, far too long for us to witness directly. Astronomers usually reconstruct stellar life cycles by studying different stars at different stages of life. But Polaris may allow scientists to watch part of that evolution in real time. Over the past century, astronomers have carefully tracked the star's pulsations. They have measured subtle changes in brightness. They have detected shifts in its pulsation amplitude. They have observed its companion stars orbiting around it. And each observation has revealed new pieces of the puzzle. Because Polaris is not alone. The North Star is part of a triple star system. A smaller companion star orbits it closely, completing a full orbit roughly every 30 years. Another companion lies far away, thousands of astronomical units from the main star. Together, these stars form a small, gravitational family moving through the Milky Way. Studying these companions has helped astronomers estimate the mass of Polaris more accurately. And that mass measurement matters for a very important reason. Polaris belongs to a class of stars known as cepheid variables. These stars pulse in brightness because their outer layers expand and contract. And more importantly, the pulsation period of a cepheid is directly related to its intrinsic brightness. This relationship allows astronomers to determine distances across the universe. By measuring how quickly a cepheid pulsates, scientists can calculate its true luminosity. Comparing that luminosity to how bright the star appears from Earth reveals its distance. This simple relationship transformed astronomy. It allowed scientists to measure the distance to nearby galaxies. It allowed Edwin Hubble to discover that the universe extends far beyond the Milky Way. And today, cepheid variables still serve as one of the most important tools in cosmology. They are part of the cosmic distance ladder, the chain of techniques used to measure distances across the universe. But for that ladder to work accurately, astronomers must understand cepheid variables in detail. And Polaris, being the closest cepheid to Earth, plays a critical role. It is essentially the reference star for calibrating the cepheid distance scale. Yet Polaris refuses to behave exactly like a typical cepheid. Its pulsation amplitude is unusually small. Its brightness variations have changed over time, and measurements of its mass have sometimes disagreed with theoretical predictions. This is the heart of the Polaris Paradox, a star that should be simple, yet continues to challenge astronomers. Solving this paradox may help refine our understanding of stellar evolution. It may improve models of cepheid variables, and ultimately, it may sharpen our measurements of cosmic distances. In other words, the behavior of a single star in the northern sky could influence how we measure the scale of the universe itself. But the story of Polaris also reminds us of something deeper. The universe is constantly evolving. Stars are born from clouds of gas and dust. They shine for millions or billions of years. Eventually, they exhaust their fuel and transform into new cosmic forms. Polaris is already well past the earliest stages of its life. It has left the main sequence. It has expanded into a supergiant star, and millions of years from now, it will evolve further still. Its outer layers may eventually drift into space, forming a glowing planetary nebula. At its center will remain the dense core of the star, a white dwarf, slowly cooling over billions of years. By that time, Earth itself will have changed dramatically. Continents will shift, species will evolve or vanish. Human civilization may be unrecognizable, if it still exists at all, and Polaris will no longer mark the north. Earth's wobbling axis will have carried the north celestial pole far away. Another star will have taken its place, perhaps Vega, perhaps some other distant star. But for now, in this brief moment in cosmic time, Polaris holds that special position, and that coincidence has shaped human history in remarkable ways. It guided explorers across unknown oceans. It inspired myths and navigation traditions around the world. And today, it guides astronomers studying the physics of stars and the expansion of the universe. A single star, 400 light-years away, quietly shining above the northern horizon. To most people, Polaris looks calm and unchanging. But we now know that beneath that steady glow lies a dynamic star, pulsating, evolving, and slowly revealing its secrets. And perhaps that is the greatest lesson of the Polaris Paradox. Even the most familiar stars in the sky may hold mysteries we have not yet fully understood. The universe is not static. It is alive with motion, change, and discovery. Every star tells a story, and Polaris, the star that anchors our sky, may be telling one of the most fascinating stories of all. So the next time you look up at the night sky, find the Big Dipper, follow the pointer stars, and look toward the quiet light that marks the north. You will be looking at more than just a navigational guide. You will be looking at a star whose rhythms help measure the universe. A star whose evolution may be unfolding within human history. And a star that reminds us how much wonder still hides in the sky above us,